So hi everyone, my name is Wachsmann, working at the German Climate Computing Center in the Department Data Management, and it's my honor today to show you a few details on what we offer for you as an analyze service, analytics service. First of all, maybe a few words how to proceed if you want to use the Ecas service here. There's on this wonderful page that Maria prepared, a tutorial or a guide through it, how to do that. I want to show you one in this quick overview here, how to do that. So first we have to get a DKZ account. That's the first step here in this quick start. Maria, do you share the links to those pages, or?
Okay, just to be super clear, this is not a session that you have to follow. Do not do what Fabian does. It's just a showing. You don't have to do this. It's how to apply to use Ecas. So you may have the links if you just go to the website, because you don't have to follow now. Do not register to Ecas now. No.
All right.
But Fabian, if you want, I can paste the links in the chat. But everything is in the page, in the website of the service. I can paste the website of the service in the chat.
Okay, I think it's a good idea to do that as well. Okay, just to speed run through that, the account you can register is on the DKZ.de page. It's the first step, so you are directed to that page. When I access the page, you can see I can already log in. But if you want to register for the Ecas service, you would have to register here with the register button. You click on it, and then you can create an account. You have to fulfill here some specifications for your email address and password of your choice, first name. And if you do that, you can then join a project. And I think if you go back to the site here, that would be the second part of the 4 steps here, where you join the 1088 project, which is the Ecas service project, and then you have to specify as the description in why you want to join it. It is in detail explained there, what you have to write and what you have to provide. The last steps here are for starting the service, and we will see how that goes in the demos and in the hands-on sessions along the way. Yeah. So let me start with what one I want to start. All right. So my demo today is about 3 parts of what we offer for you. So that. Sorry, I forget one thing. A more detailed explanation how to start Jupyter-hub and how to start a Jupyter notebook is also on the GitHub page. It's also an important link. I think it would be also good to share that once more. I can do that. It's on this ES-ENES data GitHub page here. So there you have in detail 9 steps that you can go through until you have a working notebook on the Jupyter-hub service. And also, this is the entry point for all our notebooks and our demo sessions today. But however, Marco is showing that in detail in the next demos. So let's start with Jupyter-hub. Why do we want to show you that? Why are we promoting Jupyter-hub? Jupyter-hub is a barrier-free entrance to DKZ. So you probably know that you can connect to or if you don't know, it's not so bad. You can connect to the ENES-RI, so to the high performance computing system on DKZ via a terminal interface, if you're working on Bash or Linux systems. And then you would use SSH, but this requires a bit knowledge in shell programming. Jupyter-Hub instead is a more user-friendly alternative because you can do the connections and do also working on the Mistral only via the web service or via the browser. The only thing you need is a browser and a stable internet connection. Some features that I list here, so you have and software-independent interactive access to the resources, what I mentioned earlier. So we also provide some tutorials formatted as Jupyter notebooks, so that should be easily understandable and will help you to working on the system. And another important point is that Jupyter-Hub is fully supported and maintained in Dkrz. So since you don't have software on your side, it's not such important because you don't for you because you don't have to update any software on your side, but it's important for the stable workflow at the Dkrz machine, right? So all in all, Jupyter-Hub is an advanced programming interface with a beginner-friendly control. Once more, so you would have to log in on the Jupyter-Hub Dkrz DE page here. We will show that in detail later. And then you would request a notebook server. It's in detail explained on the GitHub pages. So this is a comprehension of the 9 steps in like 2 steps here. The Dkrz then runs a Slurm job on Mistral, where a server is spawned, and it uses resources as specified as in your request. And this server runs as long as it is specified in the request. I think it's usually about 12 hours. In that time, you can close the tab in the browser and can revisit the Jupyter-Hub page, and then the session goes on and your notebook is still available. Yeah. If you have logged in and start a server, you come to a control panel where you have a graphical interface, which is Jupyter-Hub, or you can also switch to JupyterLab. If you want to know how to do that, I would recommend to go to the Jupyter-Hub documentation at that point. You can launch notebooks, but you can also launch consoles. So this is like a terminal in shell scripting. So Jupyter-Hub is the one thing, but many advantages come from the Jupyter Notebook inside that, and we do also promote Jupyter Notebooks at that point here. And this has different reasons. For example, we have that great interactive cell composition. So a Jupyter Notebook is composed by different cells, constructed with different cells, and each cell can be individually accessed and can be run without running the entire script. And a cell can also be something different than code. It does not need to be programming code. It can also be Markdown and raw text. The code language, it can be Python, or this is probably the default, but it can also be Bash or other programming languages. If you start a line in a Jupyter Notebook with an exclamation mark, the line is run as a Bash. Bash command, and the Python interpreter is not called in that point. You can also define an entire cell as Bash or LaTeX with a magic double percentage sign at the beginning. I show you now in examples how that works. So this is the basic Bash command here, the ls, which shows you the files in a directory. And since I'm working on the GitHub repository, there are lots of notebooks in that directory where I am. This would convert the entire cell to a Bash cell. It does completely the same as the cell above. And this is a way how you can show LaTeX in a Jupyter notebook. what I wanted to say also is that what I'm showing here is actually a Jupyter notebook. So if I exit this cell presentation mode here, you can see this is a notebook, and this is also available in the repository in the GitHub. All right. This presentation mode is also one extension of Jupyter Notebook and Jupyter Hub. So you can install extensions to the Jupyter Hub that makes it even more greater. And yeah, both Jupyter and Python benefit from the quickly evolving package universe of Python. So whenever you think you have to write a script for something, please check before whether there is a Python package already available in the Python universe. You can embed HTML to the notebook and other stuff like automatic code formatting when executing cells. So this is an example how you can load HTML to the notebook, and this is directly visualized in the notebook if you execute the code. And yeah, so I did that, but why isn't it shown? Something's wrong. Oh, that should actually work, and then you should see the GitLab pages for the Jupyter Hub. This is the documentation for the Jupyter Hub. Last but not least, you can select different kernels which contain different software environments. You can also install customized software environments and load that kernels for your Jupyter notebook, so you can customize your Jupyter notebooks there. On Jupyter Hub, you can choose between a handful of different configurations. So there's already presettings for those software environments, and you can change that when you are in the notebook. So you don't have to think about that before you run the notebook. You can still change that in the notebook. All right. So far for Jupyter Hub and Jupyter Notebooks. Yeah, in conclusion, Jupyter Hub is your laboratory in the web browser. So we're moving now on to Intake ESM, which is a Python package that you can use inside your Jupyter Notebook. Intake ESM is actually a plugin for Intake, so basic software development stuff here. It uses other Python packages as pandas and X-Array. If you've not heard of it, they are really great tools. I can recommend to look into that. But you can also work with Intake ESM without knowing about that packages. So what does Intake ESM? Intake ESM allows you to use collections of climate data easily and fast. I'm going to tell you why that is. So Intake ESM has different features. One important feature of Intake ESM is that you can display catalogs as clearly structured tables inside the Jupyter notebook. And that makes investigation of those catalogs really easy. And I directly start here with the example. So if you import Intake to your notebook and then open a data store from pool data, you can open the catalog and look into the data catalog with the underlying data frame here and just showing the first entries with head. If you do that, this is the output. It's going to be shown if you execute the cell here. And you can see that's a big table with different columns. And since it's only the head, we see like 4 rows here. And this is the CMCC catalog here for the Mistral, for the Dkrz system. But you can also like directly load other catalogs from the web, for example, for Google or Amazon cloud storages, for example. This is also possible with Intake. You then can browse through the catalog and select the data that you need, and you don't need to be on the file system. So if you have access to this catalog. If you download the catalog or something, you can browse the catalog without being next to the data. And that makes this cataloging software package, Intake ESM, a Pythonic reproducible alternative in comparison to complex find commands or GUI searches. Whenever you do a GUI search, it's hard to like share that result with others. In that case, you can just simply share the script, and no need for file system. How does it look like? You do a call.search. So you have an object that so this is actually the catalog object call. We have opened that in the cell before. And then we can perform a search command on that. We can specify the values for the attributes, which are the columns in the catalog. In that case, we specify an experiment. We specify also sources. And then we look into the catalog and search for the resulting data sets. And this is the result. We get one data set with 33 assets, which are 33 time ranges or paths. So these are actually files on the system. Another great feature is that you can open the data in a analysis-ready form, or as analysis-ready as possible, because those will then be dictionaries of X-array data sets, and you can directly work with these X-array data sets. And that probably helps you because you don't need to merge files. You can directly open them as an entire data set with X-array, and that leads to a reduction of temporary steps and reformatting steps. How does that look like? So we have our tasks, which we have searched in the cell before, and then we can perform the toDataset dictionary method here, and the result is actually an X-array data set for the entire time span of the experiment, which are 1980 time steps here. It's going from 2015 to 2014. So we opened a lot of files as one data set with X-array here by that function. So all these features make Intake ESM reduce the data access and data preparation task on your side. It helps us to better distinguishing between who is the data curator and who is the data analyst. I think due to time reasons, I will skip how the catalog is actually created. Yeah, maybe this is important here. What we are doing for you as services is we make catalogs available under the /pool/data/catalogs path. You can find different catalogs for different projects there, and it will grow in the future. We create and update the contents of a catalog of a project regularly. For CMCC, we do that on a daily basis with cron jobs. So cron jobs are automatically executed jobs. That means that the updated catalog replaces the outdated one. We also upload the catalog to the Swift cloud. And in the near future, we also provide a catalog that tracks the data which is removed by the update. So this is something we have on our list, but right now it's important that you save a subset of your catalog in order to make your results reproducible. Okay, and some best practices and recommendations. So one goal or an objective of Intake is that the scripts that you run with Intake should be reusable. This is the case if you really start from a catalog and don't start from temporary files. And reusable means in that case that you share your script with another scientist, and he can run that script directly without changing like path or file names. If you do start from an Intake catalog in the beginning of your script, that is the case. Yeah. So the reason why we replace with an update the outdated catalog is that you can check for new ingest into in the data pool by just repeating the script. So, for example, for CMIP6, we update the catalog on daily basis. So if you just repeat the script tomorrow, you may find new data sets in the catalog, and it will automatically be added to your script if you work with the catalog. Yeah, be careful when you load a lot of data sets with 2-dataset dictionary. Of course, as Stefan mentioned yesterday, ENES-RI doesn't load the data directly. It starts with loading the metadata, so you can work on the metadata. But if you finally want to perform analysis on the data sets, be careful with your memory, because it is easy to exceed this memory limits. All right. Okay. And now a few words, wait for it, about the data pool and the data pool content. Why am I starting? So here. We have different climate data and climate data collections in the data pool. Highlights of these climate data collections are those 4 projects. The most famous ones, I think, it's CMIP6, which is the recent phase of the coupled model intercomparison project, the databases for the IPCC report, CMIP5, which is the phase before CMIP6. Then we have Codex data, which is the coordinated regional downscaling experiment, which is pretty similar to CMIP, but on the regional scale. And we have also Area 5 data, weather data, and we provide a first catalog for that. Also, I'm not sure if it's available. I would change it. If it's not available right now in the pool, we're going to do that. Okay. So in the example of CMIP6, I want to show you how you can understand the data you're working with, so actually the content of the catalog, for example. CMIP6 is right now the most recent and largest data repository at Ecas. It contains 4 petabytes of data. 1.5 petabytes were originally published at the Ecas site. 2.5 are replicated data from other data nodes. So if you never heard of CMIP6, CMIP6 is therefore answering 3 major questions. How does the Earth system respond to forcing? So they are really generally formulated here. CMIP6 also wants to improve models. So it's searching for origins and consequences of model biases. And it's also looking into the future by assessing future climate changes, given the internal climate variability, predictability, and uncertainties. I think we have seen this picture here already. CMIP6 has a framework where other model intercomparison projects are like endorsed to CMIP6, and they focus on specific topics, which are here the fractions of that disk. For example, we have scenarios here as a topic, and this is actually an endorsed MIP, scenario MIP. It's an activity for CMIP6. In the center of the in the center of this disk, we have the simulations that every model has to perform to be part of CMIP6. So this is like the entry card for CMIP6. It contains the control run, the pre-industrial control run, for example, but also some CO2 runs. If we want to understand CMIP6 data, we need to understand a few things of the CMIP data standard. CMIP data standard defines required attributes and defines also controlled vocabularies where those attributes are described. Some of the required attributes are predefined. For others, we can register values. For example, there's a model attribute and an institution attribute, and you have to be registered in this controlled vocabulary to be a valid value that has different reasons. For example, the models need to be citable. For many attributes, a short form with a suffix _ID exists, and a longer description, we are probably working only with the short form, the IDs. And those are some important required attributes to understand what's going on. So the activity ID is actually the endorsed MIP. We have seen that in that picture above. It's a fraction of the disk. So such an endorsed MIP investigates a specific research question, and it defines experiments and requests data for it. So all the data that you find inside the CMIP6 database, it is because an activity has requested it from the models or from the participants of the CMIP6. Yeah. Source ID is the ID for the system model that has produced the data. Member ID is an ensemble member description. So all values, or all members of this ensemble should be statistically equal in that sense that you can do statistically analysis on that. For the time being, that is all what you have to know about that. I mean, we can go in detail, but that's a bit complicated. So we now use intake to investigate a bit the pool, the CMIP6 data pool. So we can look for unique activity IDs in the CMIP6 catalog. And we will see that there are 19 of those MIPs. For example, AirChem MIP, which is about analyzing aerosols and chemistry experiments and questions about that. And also scenario MIP. Most important is CMIP. CMIP contains all the basic experiments from historical over PI control and others. And then scenario MIP, which contains the scenarios for the future. How many sources do we have in the CMIP6 data pool at Ecas? We can do the same with unique source ID here. And the result is 100. Exactly 100 sources have contributed to CMIP6. Here's, for an example, just the value of a member. So the member is this RIPF formatted value here. And those are all integers after the character. I do not want to go in detail at that point. So maybe we can skip that. Not really. So one point to the terminology. So when we're speaking about a data set, we mean actually all files that cover the entire time span of a single variable. So we do not mean, we do not necessarily mean one file, because a data set can contain of multiple files. A set of required attributes define a data set uniquely. So if you have all those required attributes specified, you'd find exactly one data set. And this set of required attributes is called DRS. If you see that, that's the only thing you have to know about it. So if you arrange those elements in a specific way, you have a hierarchy, and this is also the path template for CMIP6, which looks like that. And I want to give you some hints here, because it's it can be misleading, this hierarchy. So what is unique in this hierarchy? So an experiment is definitely defined by one specific activity ID. When you're looking for the historical experiment, I'm going to show that. Also, variable IDs can be multiple in different tables, but there's only one variable ID in one table ID. And also, there should be only one version accessible and published to a specific time and point in time. Here's an example. So if you look for experiment ID historical, you'll see that there's only one activity ID called CMIP. If you look for the variable TAS in the data catalog, and you then perform the unique method again for the attribute table ID, for the column table ID, you find TAS is actually available in many of the tables, and those tables are collections of variables for a specific frequency mostly. There are also some other descriptions for it in this table ID here, but it's mostly the frequency. So for example, in 3 hour, you find 3-hourly model output, while you find monthly model output in the AMON table. This is predefined by the project, and there's no really a clear structure behind the table ID name. So if you perform the search here with both attribute specified variable ID and table ID, you find exactly one variable. All right, so I think I'm a bit over the time. Not unique in the CMIP data hierarchy is institution ID for both source ID and experiment ID. This is because different institutions may have used one specific source ID. So it's not forbidden to use, for example, EOSC from I don't know, maybe we use better the MPI model here as an example. So it's not forbidden for the DKZ to use the MPI ESM model for a specific experiment. And then if DKZ has used it, it wants to be visible as an institution, to be acknowledged for that, of course. That means if you, for example, search as a catalog with source ID MPI ESM and in a specific experiment, and then you cap the unique, you grab for the unique institution IDs, you will find everything but the MPI-M, the Max Planck Institute, which has originally developed the model. This is pretty misleading, I think, and this is why I recommend to not use institution ID if you're not exactly sure about what you want to search in the catalog. Also, if we focus on the member ID, you might think that the default value here in the member ID is always with the 1, but this is also misleading because some models haven't used the R1, I1, P1, F1 name for the member ID. All right. And last but not least, last slides here. If you don't know how the variables are called in CMIP, and you have no idea about these short names for the variables, here's a short guide how to find the correct CMIP variable name. So first of all, it's not bad to know the climate and forecast convention because there are standard names defined. Standard names are really names that should not change over the climate and forecast data supply. For example, also they are also very descriptive. So, for example, for temperature, the standard name is air temperature. And if you know this, the standard name, there's a great web tool here on the CEDA page, which allows you to search the entire CMIP data request for such standard names. If we here provide like air temperature, I specify that in this standard name table, we have actually still a lot of entries for those for this standard name, but we also find TAS here, which is the temperature at surface. I think this can be a way to go to find the variables that you need from the CMIP data collections if you don't know the names. All right, so that was my part here. And I think we can skip all the other things. Thank you very much. And I think Marco will go into detail how you can execute those notebooks and work with X-Array also.
Can you hear me? My name is Marco Kulueke, and together with Fabi, Maria, and Stefan, I'm working at the German Climate Computing Center in the data management section. And I'm going to show you an example what you can do with our service. You can find this notebook in our GitHub repository, which also has been sent to you via email. And before we go through the notebook, a brief introduction. This notebook targets beginners and encourages them to view, analyze, and visualize data on our high-performance computer instead of their own laptop. This Jupyter notebook is going to use Intake ESM and X-Array. And moreover, it's going to use hvplot, which produces nice visualizations, which you can save to your local computer and attach to reports or do whatever you want with it. So before we go through the notebook, I will briefly summarize the scope of this notebook. I have to mention this notebook is not about the science, it's more about the methods, and it's meant to give you an inspiration what's possible with our data on Jupyter-hub. So this notebook enables the user to calculate the number of summer days for any given location and any year in the past or the future using our CMIP6 data pool. So the workflow is the following. The notebook accesses the CMIP6 data pool, which Fabi presented. The notebook is doing so by using intake. And then the notebook does a simple calculation using ENES-RI, and in the end produces a visualization using hvplot. Okay, I prepared a live demo, and yeah, let's jump into it. So we're going to load some packages. I already did that. There's not much magic behind. And then you have to define some details. So first you have to define which experiment you want to use of the CMIP data pool. And as you can see here in this drop-down menu, you can choose between the historical experiment or any future projection. And there we distinguish between different shared socioeconomic pathways. In this case, we are going to calculate the number of summer days for a year in the past. So we choose the historical experiments. In the next cell, we have to define the place. As most of us organizers are based in Hamburg, we're going to choose Hamburg. And we select the year 2000. All right. In the next cell, the user will get a kind of information. That cell is asking, do you mean Hamburg in Germany? And then it also gives the coordinates. And as confirmation, you can also see the location you chose on a map. Looks right to me. So we can continue and load the intake catalog. I already did this because, as Stefan mentioned yesterday, it sometimes takes a while. This took around 45 seconds. So I already executed this cell, and then we can look at the beginning how the catalog looks, and we see in the columns the activities, the institution, the source ID, the experiment member, the member ID, the table ID, the variable ID, and much more. All right. Yeah, this catalog is huge. So in the next step, we are going to browse through the catalog. And the most elegant way by doing this is by defining a search dictionary. So in this search dictionary, you define which source ID you want to use. So source ID means climate model in this case. And I predefined the climate model of the Max Planck Institute in high resolution. Then you have to define which variable you want to use. Fabian also mentioned the website, which can help you to find the right variable name. In this case, we are going to use TAS-max. TAS means temperature at surface, and max means the maximum temperature, because we want to calculate the number of summer days. We want to have a daily frequency. We already chose the historic experiment in the drop-down menu, which is the experiment box label. And we choose one member ID, so one ensemble member. All right, now we are going to browse through the catalog. And this is our search result. So now all the results are from the MPI ESM model. We only have historical experiments. We have this member ID, daily frequency, and the variable we are looking for. And yeah, the difference are the years. So each file covers roughly 5 years. So this makes, how many files do we have? 32 files. So the most recent year of the historical year 2014. And yeah, here you can also see the file path where you would find the file. But the most elegant way to access those files would be to create a dictionary out of this result. What's going to happen here? Again, this might take some seconds, but we have time for that. Done. So, and at the next step, we are going to write all those files into one object, which you can see here. So now we have one object which is pointing to all those files, which has a size of 17 GB. So believe me, you don't want to have that on your local computer. And you can also already see the metadata, which is always important to know. So you can see the standard name, then the long name, the daily maximum near surface air temperature, which is exactly what we were looking for, and the units in Kelvin, very important. All right, and the next step, we are going to select the year. As you remember, we were selecting the year 2000, which is represented by the value of the box, of the year box. And now we reduced our data to 100 megabyte. We have the year 2000 with 366 time steps, so 1 time step per day, and 2000 has been a leap year, so we have 366, and a resolution of 192 latitude grid points and 384 longitude grid points. As we're working with climate models, now we are comparing the location of the grid cell with the location we actually choose. And this is also important to know. If you're working with climate models and you want to know the temperature or the climate at a certain point, you never get exactly this point. So in this case, the closest grid cell center would be somewhere between Hamburg and Lübeck. Yeah, this is an important information for people who are new with climate models. Yes, and the next step, we simply calculate the number of summer days. So according to the German Weather Service, a summer day is a day in which the maximum air temperature is at least 25 degrees Celsius. So for this, we calculate the temperature from Kelvin, which has been the unit of the temperature, as we could see in the metadata, to Celsius. And then we draw the temperature time series over the year 2000. As you can see, the temperature is highly variable, but usually higher in summer than in winter. And we also draw the 25-degree threshold. So this is an interactive visualization with HV plots. So it means we can zoom in if we want. And we see that in June we had some days above 25 degrees. Then the July has been pretty chilly. And then in August, again, we had some days above 25 degrees Celsius. So you don't want to count all those days. So you just use X-ray for simple calculation. So you simply count all those days above 25 degrees, and then you calculate the number. And you might wonder why it takes so long, because it looks like a pretty small data set. But up to now, the data set has not been touched. So now the calculation takes place. And yeah, you see as a result, in year 2000, we had 15 summer days in Hamburg. All right. Yeah, now you can feel free to access the repository, try it by yourself for another location. Yeah, but for this, yeah, you have to apply for an Ecas account and then feel free to play around with it by yourself. And yeah, this brings me to the end of my demonstration. And now I'm giving the presentation to Peter Calvera.
All right, let's see. Okay, I wanted to give a quick introduction of some of the work we've been doing on ESM Tool. what you should be able to see now is that I have been logged into the Jupyter Lab interface in at the DKRZ actually, and you can see these are all the different Python and different compute environments that you can load. So this has already been mentioned. You can load notebooks, consoles, etc. But what I wanted to highlight here is that for my account, I have two kernels that are not available by default, which are ESM-Volatile kernels. And for now, I have installed these kernels for my own user, but we are also trying to make this available for everybody. So maybe in a month or so, you should be able to see this ESM-Volatile kernel as well. Now, what is ESM-Volatile? I want to show you very quickly. So this has also been mentioned already, but ESM-Volatile is basically a tool that stores and executes climate analytics workflows. So if I try to do a rather complex analysis and you want to reproduce this, one way is to read the paper and try to repeat all the steps step by step and re-implement all the code. But another idea would be to just share the code, and ESM-Volatile is one way to do that. You can have a look at the ESM-Volatile documentation to look at the available recipes, for example. So a recipe in ESM-Volatile is one of these workflows. And there's actually quite a lot of them. And we have been working on making these available through the Jupyter Lab environment as well. And this is great because all those recipes need a lot of climate data, and that's exactly what is so great about this infrastructure. So if you start one of these notebooks with an ESM-Volatile kernel, yeah, you can just explore it. And I already ran this before to make sure that it goes a bit quicker, but you can just import the tool, and I'll just very briefly go step by step through what I'm doing here. So ESM-Volatile comes with a configuration, and let's just have a look at it. Normally, you should not have to worry about this, but I wanted to highlight that there's a couple of paths defined here. So this is slightly different than the intake method, although, well, in other respects, it's quite similar. But by default, I've already made sure that the settings for finding the data for different CMIP projects, for example, already points to the right location on the DKRZ machine. So ESM-Volatile should be able to find that. As I said, normally this should not be anything you want to change about that, but if there happens to be anything you want to change, this is possible. So for example, you see here this max parallel tasks parameter. I'm not going to explain what it means, but I can show that I can change it. So if I set it to 3, for example, you can see that it's now changed. So that's the configuration. But now the interesting part. So let's have a look at all the different recipes that are available in ESM-Volatile. So if I just use this command, get all recipes, you can see this enormous list of recipes that's available. And these are just workflows we can import and immediately try to execute. For this demo, I wanted to have a look at the example recipes. So I'm going to look through all the available recipes to see which one of them are example recipes. So it's going to look through some descriptions of the recipes, some documentation, and then it should be able to find a number of example recipes. There you go. So there's about 10 of them, and I'm specifically interested in this recipe Python. So one interesting thing to mention is that ESM-Volatile can also run analysis scripts in different languages, but I think Python is by far the most popular one, so I'm going to focus on that one. So let's actually load this recipe Python and have a look at it. And if I just print it like this in the notebook, you can see that there's some documentation. So it explains what it's going to do. It plots a map of, and time series of temperature. You can see who made it and who maintains it. You can see that it's been created in the context of some projects. And well, this is an example recipe, but if it would be a workflow that's related to some important paper or something else that you've published, then you could also include references here, and those would be rendered with links to the DOIs, etc. All right, so that's fairly interesting. So let's just try to run this recipe, and I will show you what the recipe actually looks like in a minute. But so if I run this now, actually the ESM-Volatile is going to load all the input data from the disk, and it's going to repeat that workflow. And I'm first just going to look at the output. And this is really interesting because, well, now I took the very simple Python example recipe, but this should also work for most of the other available recipes. There is maybe some of the recipes require some data that is currently not available at Dkrz, but the idea is that this should work for most of the recipes because, well, on the Mistral, there you should have access to a lot of climate data. So you can see that ES-Volatile is running right now. Well, that takes a little bit of time. So in the meantime, we can have a look at what this recipe actually looked like. I copied it here. So if you look at this file, it's basically a YAML file. So that's a sort of human-friendly, readable format of a workflow. And you can see here this documentation section is actually what we've just seen in the notebook as well. So you see the authors again. Then there's a section with data sets. So this recipe actually includes two different data sets, one of CMIP5 and one of CMIP6. Then there's a section preprocessors, and there are different preprocessors. So one of them is select January. There's an annual mean Amsterdam preprocessor, and there's an annual mean global. So these preprocessors are common operations that are often done on data sets. And if I do that with my software package and you do it with your software package, this may lead to different results because the implementation might be slightly different. And the way ES-Volatile does this is it takes these common operations and it has custom functions for that. So this is one way to standardize the workflows for everybody. But of course, after doing some general operations like regridding and maybe some time statistics, you might also want to do some more tailored analytics. So for example, drawing a figure of a map. So here you can see that we are actually calling a custom script called diagnostic.py. And for the time series, note that the description said we're going to make a time series. There's also same script that is going to plot the time series. Okay, if I go back now, I think it should, you can see the different outputs. So we have some output for a map and some output for the time series. And you can see that there's different types of output. So we have an image file and a data file. And also several images for the time series. So let's look at that. If I'm gonna go to the time series script 1 task and look at the first output, you can see it's an image file, and I can actually load that, and you can immediately see the image as it was produced by ES-Volatile. If we look at a data file, so let's take, for example, the second one. Oh, wait. Map as well. This is the map, and this is a data file. So this is actually the data underlying this map. But maybe I think this figure is not nice and I want to change it. Then you would want to be able to work with the data as well. And this is also possible because now we can say, okay, we want to take this output and then use load Xarray, for example. And that takes a second. But then you can see that the process data is actually loaded into Xarray and you can immediately operate on it. Xarray is not the only package to work with NetCDF data. So if you prefer Iris, for example, that's also possible. It's a very similar package, but it looks a little bit different. And if we continue to work with the Xarray datasets, for example, I can plot it interactively right now. And well, this is just to illustrate that there's many things you can do with this. Yeah, so that's it. I think so the gist of this is that you can take someone else's workflow, reproduce it entirely by running it, and then build upon it by interactively further analyzing the outputs. There's more advanced things that you can do with this as well, but if you're interested in that, please have a look at either the ES-Volatile documentation, or you can always contact me at this email address. That's it.